Hey guys, my name is IBM, and a lot of you have been asking me to record tutorials for the topics of AS and A levels. So I'm starting with A level physics, and the tutorials are in PowerPoint. They may not be free because it took me a lot of time to prepare these slides. So I don't think they are free. They will be at a cost, but the YouTube videos are going to be entirely free. You can watch the videos with a summary book and make your own summarized notes. So I would like to take you to the introduction of physics A level. This is the Cambridge International Education curriculum, and this is going to be Physics 9702. This is paper 4. This is 2024. So here is a course outline of the topics that you are most likely going to find in your class or that are going to be taught to you in Physics 9702 A level. The topics would include um, circular motion is most likely going to be the first topic, followed by gravitation, followed by ideal gases, followed by temperature, followed by thermodynamics, so we shall have simple harmonic motion, oscillations, expect to see electric fields, expect to study magnetic fields and electromagnetic induction, you expect to study capacitance, you expect to study alternating current, nuclear physics, quantum physics, astrophysics and cosmology, and lastly we expect to study physics. When you cover these 12 chapters in your A-level physics, it means you're already perfect. But for these tutorials, I'll start with nuclear physics because nuclear physics has a link. Nuclear physics has a link to the last topic that we covered in your physics AS level. So this is nuclear physics. Remember, this is A-level physics 9702, and of course nuclear physics is part of paper 4. Let this be lesson number 1. What is wrong with this? So this is going to be lesson 1, and without wasting time, let's dig deep into the lesson. Let's start nuclear physics. So in nuclear physics, the first thing we need to think about is going to be the mass excess. I want you to recall from particle physics that an atom may be modeled as massive but very small positively charged nucleus and surrounded by negatively charged electrons. If you recall, J.J. Thomson's model, which was rejected, it was superseded by the nuclear model by Rutherford after the famous alpha particle scattering experiment. So it was later on agreed that the nuclear model can be acceptable because of its several advantages. So from the nuclear model, we know that an atom has a positively charged nucleus, and this positively charged nucleus is surrounded by negatively charged electrons. Let's think of a carbon-12 nucleus. A carbon-12 nucleus consists of 6 protons and it has 6 neutrons. When the stable nucleus and the respective component neutrons are put on a scale, as demonstrated by this picture here, the balance is observed to tip to the side of the component neutrons as shown by this picture here. So the question is why should why should the balance tip towards the side of the 6 protons and the 6 neutrons, which are the nucleons which were got from the carbon-12 nucleus? Imagine you break an object into 2 parts, for example, and then it weighs the total mass of the 2 parts is greater than the mass of just the object as it was before breaking it into 2 parts. So this is exactly what is observed when a stable carbon-12 nucleus is split into its constituent nucleons, that is the 6 protons it contains and the 6 neutrons it contains. Experiments show that the total mass of the 6 protons plus the 6 neutrons is greater than the mass of a stable nucleus of carbon-12. The separate nucleons have a total mass more than or greater than the nucleus itself. So you might ask yourself a question: why is the mass of the nucleus less than the total mass of its constituent protons and neutrons? Why is it that if I break an object into several pieces, the total mass of the pieces appears to be greater than the mass of the object before it was broken into pieces? So this is the argument here. Why is the mass of a nucleus of carbon-12 less than the total mass of its 6 protons and 6 neutrons? That is now the question here. So I want you to think of carbon, for example, as being a stable nuclide, which means that nucleons are bound tightly together or are held tight together by a force which we call the strong nuclear force from particle physics. So in order to pull away or in order to pull the nucleons apart, you put in energy. The only thing we do to separate the nucleons which make up carbon-12 is putting in energy. In other words, we are doing work against the strong nuclear force which holds the nucleons together. So the only force holding the nucleons inside the carbon-12 nucleus together is the strong nuclear force. In order to separate the 6 protons and the 6 neutrons further away from each other, we have to add in energy. So now the question is, where does the excess mass come from? Where does the excess mass come from? This is going to be addressed shortly. But of course, after the mass excess, we shall explore nuclear binding energy and we shall also explore radioactive decay. So previously, I've just asked, where does the excess mass come from? We have said to separate the nucleons further apart, the only thing done here is adding in energy to overcome the strong nuclear force, using energy to do work against the strong nuclear force. So this leads us to the famous Einstein's equation of 1905. We can think of the fact that since we have only added in energy and energy has resulted into a total mass which is greater, then we can say maybe energy and mass are equivalent in some way. And that equivalence was given by Albert Einstein in 1905. This is what we call the mass-energy equivalence. That is, energy is equivalent to mass by an equation given as E equals to mc squared. So the total mass of the nucleons will therefore be more than the mass of the nucleus because the difference in mass is going to be compensated for by addition of or the energy which has been added. On the other hand, if we bring protons and neutrons together to form a stable carbon-12 nucleus, again, observations show that the nucleus which is formed weighs again less than the total mass of the nucleons which formed the nucleus. Does it mean that energy has mass? Maybe. So we are saying mass and energy are going to be interchangeable. A difference in mass can be compensated for by emission or addition of energy. A difference in mass can be compensated for by emission or addition of energy. So that's why a layman would simply say, it seems like energy has mass. Does energy have mass? We shall explore that in more details. For now, let's explore mass excess in details. We have said a carbon-12 nucleus has 6 protons and 6 neutrons. These combined form a nucleus, but the total mass of the 6 protons and plus the total mass of the 6 neutrons is greater than the mass of the stable carbon-12 nucleus. So there is a difference in mass, and that difference in mass is going to be called the mass excess, or which we shall sometimes call the mass defect. The difference between the mass of the individual separate nucleons and the total mass of the individual separate nucleons and the combined mass of the nucleus itself is going to be called the mass excess or the mass defect. So this is when the protons and neutrons come together to form a nucleus. I have said that the mass of the nucleus is less than the sum of the masses of separated protons and neutrons. This difference in mass is what we are going to call the mass excess or the mass defect of the nucleus. So, because there's a difference in mass on both sides, that is total mass of the protons, or protons and neutrons, and the mass of the nucleus. So it means the mass excess or mass difference is the total mass of the protons and neutrons minus the mass of the stable nucleus, which can be represented by this equation here. So Z is going to be the number of protons and N is going to be the number of neutrons. Of course, MP is going to be the mass of a single proton and Mn is going to be the mass of a single neutron. M nucleus is going to be the mass of a stable nucleus. So we now know what we mean by mass excess. So Z is going to stand for the number of protons, N is going to be standing for the number of neutrons. Of course, MP is going to stand for the mass of a proton, and Mn is going to stand for the mass of a neutron. M nucleus is going to stand for the mass of the nucleus. So that is the difference between these two total mass of these are called the nucleons. The difference of total mass of the nucleons minus the mass of the nucleus is going to give us the excess mass or the mass excess as shown there. Okay, so why is there a difference in mass? That could be the question you should be asking yourself. Why the difference in mass? Why is there a difference in mass? That is the question you should be asking yourself. Why the difference in mass? So, carbon, for example, being a stable nuclide, it means that the nucleons are bound tighter together by the strong nuclear force, as I've already mentioned. And in order to pull the nucleons apart, energy must be put in. In other words, work must be done against the strong nuclear force which holds the nucleons together. But by the mass energy equivalence that we have mentioned from the famous Albert Einstein's equation, the total mass of the nucleons will therefore be more than the mass of the nucleus, because in separating the nucleons, energy has been added. And since energy is equivalent to mass by that equation, E equals to mc squared, then that energy added is compensated for by the difference in mass. So that means the total mass of the nucleons, where energy has been put to break or to separate them up, to separate them, results into the excess mass we are talking about in this case. So when protons and neutrons come together to form a stable nucleus, that is a stable carbon-12 nucleus, energy is given out or released on formation of the nucleus, and since E equals mc squared, there is a reduction of mass. So mass of the nucleus formed will be less than the total mass of the nucleons themselves. So in separating the nucleons, energy is added, which results into excess mass of the nucleons. In bringing the nucleons together to form a stable nucleus, energy is given out. Because energy is lost, it means total mass of the nucleus formed is going to be smaller. That is what we are calling the mass defect or the mass excess. So let's talk about what we call the atomic mass unit. Atomic mass unit. Atomic mass. At nuclear level, the mass of the nuclei and the nucleons are so small that the unit kilogram The unit kilogram is going to be too big, and of course, it is going to be too clumsy to use at nuclear level. Imagine the mass of a proton is 1.672623 times 10 to the power of minus 27. That mass is too small to use the unit kilogram. Instead of using a very large unit kilogram at nuclear level, another unit called the atomic mass unit is normally used. One atomic mass unit is defined as being equal to 1/12. One atomic mass unit is defined as being equal to 1/12 or a twelfth of the mass of carbon 12. 1/12 of the mass of carbon 12. In other words, 1/12 times the mass of a carbon 12. This results into 1U as being equal to 1.66 times 10 to the power of minus 27 kilograms. If you try to check using a calculator, if you try to divide 1.67262 times 10 to the power of minus 27 kilograms by 1.66 times 10 to the power of minus 27 kilograms, you're most likely going to get 1.007276U. If you try to divide the neutron mass of 1.674929 times 10 to the power of minus 27 kilograms by 1.66 times 10 to the power of minus 27 kilograms, you're most likely going to get to 1.008665U. If you try to divide electron mass, to divide electron mass by 1.66 times 10 to the power of minus 27 kilograms, you're most likely going to get 0.00549U. So when you look at these values, you notice that if they are expressed in the atomic mass units, they are a little bit fine and they look good, if I'm to put it like that, rather than putting the unit kilogram on something which is very, very, very small. So the unit atomic mass unit is very important in this case. So somebody may be asking themselves, how is the atomic mass unit equivalent to 1.66 times 10 to the power of minus 27? So having seen what it is equivalent to, or having seen what one atomic mass unit stands for, as 1/12 of the mass of a carbon 12 atom, then let's try to establish and see how is one atomic mass unit equal to 1.66 times 10 to the power of minus 24. So let's try to show that 1U equals to 1.66 times 10 to the power of minus 27 kilograms. That's what we want to show now. I'll pick my pen. Change the color to blue. So how is 1U equal to 1.66 times 10 to the power of minus 27 kilograms? That constant is always given in the list of constants. So by definition, we have that 1U is equal to a 12th. 1U is equal to 1/12 of the mass of an atom of carbon 12. 1U is equal to a 12th of the mass of an atom of carbon 12. So we want to find the mass of an atom of carbon 12 from a unit called ideal gases, which I'm very certain that you'll soon be studying. If I write carbon 12 as C12,6, that is carbon 12. It means 12 grams of carbon 12, 12 grams of carbon contains, because 12 grams, that is 1 mole. 12 grams of carbon 12 contains, it contains 6.02 times 10 to the power of 23 atoms. That is what you call Avogadro's number, Na, under ideal gases. So 12 grams of carbon 12 is 1 mole, and 1 mole contains 6.02 times 10 to the power of 23 atoms. So how about what is therefore the mass of one atom? So one atom, so I will say mass of one atom equals to, because 12 grams contains that number of atoms, so that means one atom has a mass of 12 grams divided by 6.02 times 10 to the power of 23. So that is going to be the mass of one atom in grams. So if I change it to kilograms, it means this is going to be equal to 12 times 10 to the power of minus 3 divided by 6.02 times 10 to the power of 23, and this is going to be in kilograms. So that is the mass of one atom of carbon 12. So it means 1U is going to be a 12. That is 1 over 12 times the mass of one atom of carbon 12, which is 12 times 10 to the power of minus 3 divided by 6.02 times 10 to the power of 23 kilograms. So I'll check with my calculator. I don't know why my calculator does not show on this screen when I'm using PowerPoint. But I'll just press my calculator. You can also check yours. Of course, 12 has cancelled here. You remain with 1 times 10 to the power of minus 3 divided by 6.02 times 10 to the power of 23. This is in kilograms. So I'll just press my calculator. So I have that 1U is equal to 1.661 times 10 to the power of minus 27 kilograms. And of course, in the list of constants, normally it will be quoted as 1U being equal to 1.66 times 10 to the power of minus 27 kilograms. So that is 1U. So note that I've shown that 1U is 1.66 times 10 to the power of minus 27 kilograms just from the definition of the unified atomic mass unit, which states that 1U is a 12th of the mass of an atom of carbon 12. And we said if we have carbon 12 as that, the nucleon number is the mass in grams, and that is equivalent to 1 mole. So 1 mole of carbon 12, which is 12 grams, contains the Avogadro's number, which is the number of atoms contained in 12 grams of carbon 12. So we could find the mass of one atom by dividing 12 grams by total number of atoms in 1 mole. So we found the mass of just one atom. Then we substituted in the definition of the atomic mass unit as being a 12th of that mass, which gives us 1.66 times 10 to the power of minus 27 kilograms as required. Example, calculate the mass defect for nitrogen-14 nucleus. The measured mass is 14.003. Let me get my pen back. 14.003070U. They've given us the mass of a proton as 1.007276 U. Mass of a neutron has been given as 1.00888665 U. So I don't have enough space. I'll just work this out from here. We want to find the mass defect. Remember I said mass defect is just the difference in mass. So I'll use this space because I don't have enough space. So it is nitrogen 14,6. So this is 6 protons and it has 14 minus 6. That is, I think that is 6 protons and 14 divided by 6. Those are how many? 8. 8 neutrons. So remember, mass defect is the difference in mass or difference in the mass between the total mass of the nucleons and the mass of the stable nucleus. So I'll say mass defect is going to be, so I have 6 protons, so I'll say 6 times the mass of 1 proton, which is 1.007276 plus there are 8 neutrons, so I'll say 8 times the mass of a neutron, which is 1.008665. That is total mass of the nucleons minus the mass of the nucleus, which mass of the nucleus is 14.003070. So we are getting total mass of the nucleons minus total mass of minus the mass of the stable nucleus. So I'll just check my calculator. I think in the next video my calculator will be able to display on the screen. So pressing my calculator, let me just press my calculator. You can also check with your calculator. Okay, so from my calculator, the difference in mass, which is the mass defect, is 0.10976 U. So this is the mass defect in unified atomic mass units. Calculate the mass defect for a helium nucleus. Helium is He42. For us, many times they will give us the notation or the formula, but for simpler nuclei such as helium, they expect us to be knowing them. So helium has 2 protons plus 4 minus 2. It has 2 neutrons. So we want to find the mass defect. So I'll simply say mass defect is equal to the total mass of the nucleons, which is 2 protons, 2 times the mass of 1 proton, so that is 2 times 1.007276 plus 2 neutrons, 2 times 1.008665. So this is total mass of the nucleons minus the mass of the stable nucleus of helium, which is 4.001508. I'll just press my calculator. Okay, so to 6 decimal places, the difference in mass is 0.03037 U. So that is the mass defect for helium. Then calculate the mass defect for carbon-12 nucleus in kilograms. This time they want this in kilograms. Anyway, the masses have also been given in kilograms. So I'll just use this space here. So the mass defect is going to be the difference. Note that there are 6 protons. Carbon-12 is having 6 protons plus 6 neutrons. So I'll say 6 times the mass of a proton, which is this one here, 1.672623 times 10 to the power of minus 27 plus 6 times the mass of a neutron, which is 1.674929 times 10 to the power of minus 27. Then I'll subtract the mass of a stable nucleus, which is given as 19.926483 times 10 to the power of minus 27. So I'll just press my calculator. Okay, so from my calculator, the total mass defect is 0.15889 times 10 to the power of minus 27 kilograms. It is 0.15889 times 10 to the power of minus 27 kilograms. So that is going to be the mass defect in that case. So notice that to find or to calculate the mass defect or the mass excess, we just get total mass of the nucleus minus the mass of the stable nucleus. In other words, we are finding the difference in mass on both sides of an equation. For example, if it was nitrogen, the nucleus is N14,6. And we are separating this by adding energy to get the 6 protons plus the 6 neutrons. So in other words, we are getting total mass this side minus the mass the other side. So it is just a difference in mass. Okay, so this takes us to Einstein's mass energy equivalence. So we have already seen that there's a difference in mass on both sides when a nucleus is split into its constituent nucleons. And we have explained that that difference in mass is only because energy is added into separating the nucleons apart. Albert Einstein in 1905 made what we call a revolutionary hypothesis, and he suggested that energy has mass. Of course, this is not an easy idea, but when bodies are in a higher energy state, they are said to have more mass than in a lower energy state. For instance, a sack of stones at the top of a hill will have more mass than when it is at the bottom, because in taking it up a hill, it's like energy has been added to the sack. That is Albert Einstein's argument. Thus, we can say that Einstein proposed there is an equivalence between mass and energy. Einstein proposed that there is an equivalence between mass and energy. The relationship between energy and mass is given by E equals to mc squared, where, of course, c is the speed of light and E is the mass defect. I mean, E is the energy, m is actually going to be the mass defect. Of course, generally at nuclear level, since we're in nuclear physics, at nuclear level, we are always dealing with very small quantities. Therefore, we normally write delta E and sometimes write delta M, for delta E to mean change in mass or small mass, and delta M to mean mass defect or difference in mass. So the mass of a system increases when energy is supplied to it. In other words, in separating the nucleons, total mass of the nucleons is greater because energy has been added. On the other hand, When energy is released from a system, its mass decreases. We believe that when the nucleons are brought together to form a stable nucleus, energy is released, and therefore the nucleus which is formed is expected to have a smaller mass. In conclusion, we can simply say that mass and energy can be considered equivalent and interchangeable. Mass and energy can be considered equivalent and interchangeable. So we are saying mass and energy are equivalent and interchangeable. So energy has mass? Yeah, kind of. But wait, oh, I get it. I get it. Energy equals to mc squared. So these animations are communicating what exactly you might be thinking. How is energy having mass? In this part of nuclear physics, we have established that energy is equivalent to mass by an expression E equals to mc squared, according to Albert Einstein's revolutionary hypothesis. His argument is that if you take a sack of stones on top of a hill, for example, it is considered to have more mass than it was having when it was at the bottom. Reason, Albert Einstein was arguing, in taking it uphill, you are doing work against gravity, so you are adding energy to the sack of stones. In separating the nucleons, you are putting in energy to overcome the force of attraction between the nucleus. So that is the only way we can account for the excess mass given by the total nucleons. So energy is equivalent to mass by the equation E equals to mc squared. A few things we need to note here. Number one, the joule, which is a unit for energy, is going to be a very large unit at nuclear level, because we are going to deal with very, very small amounts of energy at nuclear level. So we need a more convenient unit. We need a more convenient unit at nuclear level. And a more convenient unit is going to be called the mega electron volts, which is MeV. As many energy changes that take place in the nucleus are of the order of several mega electron volts. What is a mega electron volt? One mega electron volt is the energy gained by one electron when it is accelerated through a potential difference of 1 million volts. Of course, mega stands for 1 million. Electron volts, 1 electron. So 1 volt. So 1 mega electron volt is the energy gained by one electron when it is accelerated through a potential difference of 1 million volts. Maybe just to remind ourselves of something that we mentioned in AS physics. From our AS physics, remember the definition of electric potential difference, where we defined the V potential difference as being equal to charge times accelerating. Sorry. We defined electric potential difference V as energy per unit charge. So it means the energy is equal to the charge times V. But this time it is 1 electron, and the potential difference is 1 million volts. So it's like the energy in joules, the charge is 1 electron, so that is 1.1 electron times 1 million, that is 10 to the power of 6 volts. So this is in coulombs, this is in volts. So that is what we are calling mega electron volts. So energy can be in joules if it is in coulombs times volts. But we are saying this is equivalent to 1 mega electron volts. So we are saying 1 mega electron volts is the same as 1 electron, which is 1.6 times 10 to the power of negative 19 coulombs times 1 million, which is 10 to the power of 6 in volts. And of course, this will give us joules. So it's like 1 mega electron volts is the same as 1.6 times 10 to the power of negative 13 joules. So 1 mega electron volts is almost the same as 1.6 times 10 to the power of negative 13 mega electron. 1.6 times 10 to the power of minus 13 joules. So a common question would be, show that 1U is the same as 930 mega electron volts. Having seen that 1 mega electron volts is the same as 1.6 times 10 to the power of negative 13 joules. So how do we show that 1U is equivalent to 930 mega electron volts? That's a common question in paper 4. Show that 1U, or 1 unified atomic mass unit, is approximately 930 mega electron volts. So let's show this. I want you to recall that we have already derived the fact that 1U is the same as 1.66 times 10 to the power of minus 27 kilograms. And I've said this is normally given in the list of constants. So this is going to act as our mass defect. So this means the mass defect is going to be 1.66 times 10 to the power of minus 27 kilograms. Then from Einstein's energy equivalence, energy is equal to mc squared, or energy is delta mc squared. We shall have the energy equivalence of 1U as being equal to the mass defect, which is 1.66 times 10 to the power of minus 27, then times the speed of light, which is 3, times 10 to the power of 8, and this is squared. I'll just press my calculator for this. Okay, so from my calculator, I have this as 1.494 times 10 to the power of minus 10 in joules. So it means 1U is equivalent to 1.494 times 10 to the power of minus 10 joules. That is 1U. But if I want this let me say I want this in electron volts. But 1 electron volt, of course, this is the energy gained by 1 electron when it is excited through a potential difference of 1 volt. So 1 electron volt is 1.6 times 10 to the power of minus 19 joules. That's 1 electron volt. And also, if it is mega, the potential difference is 1 million. So 1 mega electron volts is going to be 1.6 times 10 to the power of, we multiply that by 10 to the power of 6, it becomes 10 to the power of minus 13 joules. So to change that energy into mega electron volts, so we just divide that by 1.6 times 10 to the power of minus 13 joules. So the energy equivalence therefore becomes 1.494 times 10 to the power of minus 10 divided by 1.6 times 10 to the power of minus 13. And this is now going to be in mega electron volts. So I'll just check with my calculator. So my calculator is giving me 933.7 mega electron volts. Of course, this is 4 significant figures. To 3 significant figures, this would be 934 mega electron volts. To 2 significant figures, of course, this would be 930 mega electron volts. So 1U is equivalent to, so it means 1U is equivalent to 930 mega electron volts in terms of energy. I think that makes sense. Yeah, I think lesson 1 should stop there.
At 29 and I find myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we pass time, the more we need to set the rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. Life lessons come one in a dozen. The other 11 get something from nothing. I sit here looking for an answer. Maybe the biggest question was in the last chapter. You gave me the soul I have today. Without you I never could have moved away. But now I see what you teach. I do believe